Hello everyone. Now we are going to see some topics about trapezoidal and sinusoidal synchronous motor. First start with introduction. Normally trapezoidal permanent magnet synchronous motor are also known as brushless DC motors because trapezoidal motors have square waves. Trapezoidal wave magnetic field of permanent magnet synchronous motor and its rotor makes the spatial distribution of the stator and the rotor rotates counter electromotive force generated from the trapezoidal wave. And now sinusoidal. In sinusoidal, motor controllers used DC square waves or of current switched in six different states based on signals from Hall devices, each spaced at 120 electrical degrees. Today, most brushless motors of this type are driven by motor controllers using sinusoidal current control with space vector modulation. Next, let's see about the working of trapezoidal and sinusoidal motors. First, we see about trapezoidal. Working in trapezoidal motor, the winding current always showed ladder type. Type of motor is sometimes referred to as brushless DC motor. This kind of motor with control and it's low cost and it can save the speed, position sensor and so on. And its model it's using 150 kilowatt permanent magnet and we use water for cooling. However, the trapezoidal wave permanent magnet motor in principle with the inherent electromagnetic pulse that the motor torque ripple is very high. Due to the torque ripple is high and it is easy to produce noise at high speed. Low speed sheave difficult to obtain a smooth torque. And the trapezoidal wave permanent magnet motor therefore only be used in hybrid electrical vehicle attachment system due to of high noise and low speed sheave, and it is used in electrical vehicle attachments such as electric pumps, air compressors, in many less demanding non-car class areas such as electric bicycles and of the motor has a broader application. Next, we have next the topic is sinusoidal. The high performance drives of the sinusoidal back EMF type permanent magnet synchronous motor can be achieved by the current vector control where the sinusoidal currents flow according to the rotor position and the current phase is suitably controlled according to the operating conditions. In such a high performance drive system, a high resolution position sensor is required. In this paper, a sinusoidal current drive system with a low resolution position sensor is proposed. The high resolution position information is obtained by the position estimating circuit from the signal of a low resolution position sensor. The steady state and the transient characteristics of the sinusoidal waves are examined by several experiments. Then it is confirmed that the sinusoidal current drive and the high performance current vector control can be achieved by the proposed drive system. Now we see about the advantages of the systems. Trapezoidal motor torque ripple is high and it is easy to produce noise at high speed, whereas sinusoidal current control offers the most advantages in smooth motion from the smoothly rotating torque vector. And the next thing we are going to see about back EMF generation in trapezoidal motor. In a brushless DC motor, the rotor consists of permanent magnets and the stator has steel laminations with windings through axial slots. The windings are wound in a trapezoidal fashion and produce a trapezoidal back EMF. Trapezoidal drives are sometimes referred to as square wave drives, although true square wave forms are rarely used due to their sharp transition between positive and negative values. Instead, modified square or quasi square current is used. Trapezoidal commutation is common in high speed applications or where high torque is required. Trapezoidal computation is also less costly than other methods due to its simple control algorithms. In most applications, the rotor position is determined by the three Hall effect sensors that are mounted on the stator. As we already know, the rotor and the stator are 120 degrees apart. When the rotor passes over the sensor, they produce either a high signal or a low signal to indicate which rotor pole is passing over, whether it is north or south. And this change from high to low or low to high of the three Hall sensors gives rotor position information every 60 degrees, meaning that 6 steps are needed in order to complete one electric cycle. Thus, the term 6-step commutation is used for trapezoidal motors. The correct commutation sequence is determined from the combination of the Hall sensor signals. The trapezoidal commutation can also be performed based on the motor's back EMF, which allows the elimination of Hall sensors. In a typical three-phase brushless DC motor with a trapezoidal current, one winding is positive and one winding is negative and one is open. The open winding can be used to detect the zero crossing point of the back EMF, which corresponds to what would be the signal change in a Hall sensor. However, the back EMF is proportional to the motor speed. This means that hurry at very slow speeds and especially during starting, the back EMF will be very low. So the motor must be started in open loop mode until sufficient speed in the back EMF are generated. At that point, the controller can be switched to back EMF sensing for commutation, and the downside of the trapezoidal commutation is that it results in torque ripple at each step of the commutation. It means for every 60 degree. And although in theory the brushless DC motor's back EMF is trapezoidal, but in reality the back EMF waveform is not purely trapezoidal. Another thing we have to note in sinusoidal synchronous motor is back EMF generation. Now, first, let us know what is back EMF. Back EMF is a voltage generated by the rotation of the motor. It normally opposes the applied voltage according to Lenz's law, and the back EMF reduces the current flowing through the coils. Back EMF is generally be sinusoidal if the power supply is AC and trapezoidal if the power supply is DC. The stator of a AC motor has skewed magnets and overlapped windings that are sinusoidally distributed. This sinusoidally distributed AC motor has magnets results in a sinusoidal back EMF waveform. The drive current being AC is sinusoidal in nature and closely matches the back EMF waveform. The combination of the three-phase sinusoidal drive current and sinusoidal back EMF results in a very constant torque output with virtually zero torque ripple. Sinusoidal waveforms also give real AC motors high efficiency and minimum noise and vibration when compared to motors with trapezoidal current and back EMF. Sinusoidally wound motors can use sinusoidal communication in which a Hall sensor or feedback device is used to determine the rotor position and apply the correct commutation sequence. The goal of the sinusoidal commutation is to generate a rotating current vector, and the rotating current vector has constant magnitude and it is arranged in orthogonal or perpendicular to the rotor. In order to do this, the rotor position must be determined with a high level of resolution. So, resolvers or encoders are used more often than Hall sensors for rotor position detection. In sinusoidal commutation, as speed increases, phase lag begins to play a part, taking the stator or rotor fields out of sync with each other. Field oriented control avoids the speed limitations of sinusoidal commutation by directly controlling the current vector. In simple terms, this commutation means modulating the current vector on the basis of sine waves, and the vector's magnitude and quadrature direction are determined relative to the rotor. And finally, while sinusoidal commutation provides smooth motion and high efficiency at slow speeds, field oriented control allows smooth motion and high efficiency to be achieved across a wide speed range.